Section 4.2, we're going to finish working on today. We're looking at prime and composite numbers, and we had gotten through the point of taking a look at some basic and then also some more extensive factoring techniques. We had specifically looked at factoring with trees and with this division, sort of a lattice algorithm kind of thing. We had taken a look at what happens if they're already partially factored. And the answer is we don't want to unfactor them and multiply back out. That's counterproductive, so we break them down from there. And then we looked at what happens when there's a sum of different factors that are being added together. That's right. And then we're taking a look now at theorem 4.12, and this is the fundamental theorem of arithmetic. And anytime somebody puts the words fundamental theorem, it means it's really important. There's several different fundamental theorems. There's a fundamental theorem of counting. We do that one in Prop and Stat. There's fundamental theorem of algebra. You usually see it in a college algebra course. There's one for calculus. There's one for lots of different things. So this one's the one for arithmetic. So the fundamental theorem of arithmetic says the following. Each composite number can be written as a product of primes in one and only one way, except for the order of the prime numbers. So what that's telling you is that these breakdowns that we got over here are unique. The only thing that could be altered and considered maybe not unique, depending on your point of view, is if you switched them around. But I can't factor this and not get 2 2s, a 5, a 7, and 2 13s. It will always be that way. It is a unique arrangement, not arrangement, but a unique listing of all the different factors. Okay, those factors are unique to this particular number, 23,660. So that's really important. And it's also important to realize that, and we'll see it in a little bit here, that this is part of the reason why we do not want maybe the number 1 to be considered a prime number. We talked about it not being prime by definition last week, but there's actually a problem that happens if we decide it is prime. And so we'll see that here in an example in a couple minutes. All right, next theorem, theorem 414 says, if D is a divisor of n, then n over d is a divisor of n. This is actually telling us that factors occur in pairs, which we saw back in section 4.1 already, when we had a question that was about the number 24. And the question was, if the number 24 divides something, what else divides it? And we started trying to list numbers, and we listed them all. We eventually got them all. But I showed you at that point that it's easier to make sure you get them all if you put them in pairs. So this is saying something like this. If this is an example of what it's referring to. If 3 divides 24, then 24 divided by 3, what is 24 divided by 3? 8, thank you, which is 8. 8 will divide 24. And you can see then, if you take a look at these numbers, the way that they're done, is that the 3 and the 8 are pairs. 3 times 8 is 24, so 3 and 24, 3 and 8 will both divide 24. And so this theorem is really just telling us that factors come in pairs. Now, sometimes the pairs are a repeat of the factor. For example, if you did, we'll call it an example. If you did 6, 6 divides 36, but 36 divided by 6 is also 6. So 6 divides 36 again. These are still occurring in pairs. It's just that the pair is a duplicate of the same number. So they still come in pairs. It's just this one doesn't give us any new factor that we can consider if we did that one. So they all come in pairs. All right, another composite number theorem, theorem 415. If n is a composite number, or is a composite, then n has a prime factor p such that p squared is less than or equal to n. I want to read one more before we actually talk about what it means, because these next two theorems, theorem 415 and 416, go together. If n is a whole number greater than 1 and it's not divisible by any prime p such that p squared is less than or equal to n, then n is prime. Now, clearly these two must go together. They've got the same inequality in them, right? We see that same inequality showing up in each of the theorems. But what is it really telling us, or how does it help us? Because this is actually a very helpful set of theorems. This actually tells us these two items combined together, when we can stop trying to look and see if something's prime. So if you took a number that was really big, like let's say you had the number 719, right? And you wanted to figure out if it's prime or not. Well, you'd start at the beginning and you'd say, okay, well, 2 doesn't divide it. And you'd go to the next prime number, 3. 3 wouldn't divide it. And you'd go to 5. 5 wouldn't divide it. When can you stop? When can you actually say, I'm done? Guaranteed there's not one there. I mean, do you have to go all the way up to 719? And the answer is no. This actually gives us a stopping point that's much faster than you might have expected. So this one says you can stop looking for primes after you've tested all primes less than or equal to the square root of your number. So in my example, Kinsey, you got a calculator there. Actually, Kaylee does too. One of you guys, find the square root of 719 for me. Just find the square root of 719. Oh, it's your phone I was seeing, sorry. All y'all phones, I thought I was seeing calculators. I'm on a level playing field with him, I can't tell. Kaylee's got it though. It's okay, it's a decimal, it's an ugly one. What did you get, Kaylee?
The square root of what?
719, 719.
26, 80.
Okay, so my example was 719, and when you took the square root, you got approximately 26 point what? Just give me one decimal.
8.
8. This tells us that once I've tested the numbers up to 26, all the primes, if I don't find a prime number that divides 719, then 719 is prime and I don't have to keep testing. And I'll tell you what, that's not very far compared to the number 719 if I thought, oh, maybe I have to go halfway, right? 26, like that's not very many numbers. I would test 2, 3, 5, 7, 11, 13, 17, 19, 23. I think I'm done. I'd have to test 9 numbers and that's it. And once I tested those 9 numbers, if none of them work, if one of them works, obviously it's composite. But if none of them work, then the number's prime and I don't have to keep testing. This is a really good news kind of theorem because it simplifies our process a lot. So we're going to do this for the number 967 to decide whether or not this is prime. Now, it's not exactly what this question asks us to do, but we could do that for 967. This question simply asks us, what's the biggest prime that you'd have to check? Right, what's the biggest prime number, not listing all the prime numbers. So we're going to do the same thing as we were talking about with 719. We're going to take 967 and we're going to take the square root. What is the square root? Again, one decimal is enough.
31.1.
31.1. Okay, so what is the smallest prime number? I didn't say that right. The biggest prime number smaller than 31.1. Almost. 29 is a prime number underneath it, but there's one closer. It's 31. Yeah, this one happens to be 31. So we would have to test, that's the biggest number we'd have to test of prime numbers. So if we have tested everything up until 31 and 31 doesn't work, then we can declare that we know for sure our number is prime. It's good, right? It's good stuff. This is the one that I mentioned earlier, being justification for why we should be very glad that 1 is not a prime number. Okay? So this one says, show that if 1 were considered a prime number, every number would have more than one prime factorization. So we're going to just create an easy composite number to work with. Somebody give me a small composite number. Don't think too hard. 6 will work. We can go with 6. 6 is composite, right? Why is it composite? Do you remember what our definition for composite was?
It has more than 2 distinct positive divisors.
Yeah, this has more than 2 positive divisors, right? Distinct ones, yeah. So we obviously have 1 and 6, but we also have divisors. Not multiples, divisors. 3 and 2. Yeah, 3 and 2. There's 4 divisors for the number 6, okay? So if I were to write down prime factorization as we know that it works, it would be 2 and 3. And the prime factorization for 6 would be 2 times 3. Everybody agree?
Yes.
Okay, but if 1 were a prime factor, I could also write 2 times 3 times 1, right? That's another factorization, but it gets worse. I could actually write 1 squared, or I could write 1 cubed. And this would go on forever, right? So if 1 were considered prime, then the fundamental theorem of arithmetic back at the very top of this page would simply not be true. I'd have infinitely many ways to write down the factorization for every composite number. That's not very helpful, right? So the fact is that by not including the number 1 as a prime factor, it simplifies our life for factorization. We have to stop right here at prime factorization because 1's not a prime number. Okay, example 4 talks about these pairings that we were talking about. Mr. Arbor wants to plant apple trees in a rectangular array. If he has 26 saplings, find all possible numbers of rows if each row is to have the same number of trees. And we looked at arrays back in chapter 3. In 3.4, it's a multiplication strategy, right? Making an array. So arrays have to have both length and width, right? So that's the 2 pairs that we're talking about here. I'll get you started. One option, albeit a very silly one, would be that he could have 1 row of 36 trees or 36 rows of 1 tree. So these are 2 different numbers of rows of trees, depending on how you're looking at the tree row, right, that he could have. So if we go up from there step by step, what's the next option of rows he could have? 2 and 18. So he could have 2 rows of 18 or 18 rows of 2. Okay, 3 rows of 12. Now while we're going up 1, 2, 3 on the left, we're coming down on the right and we're narrowing down our different numbers of options. So this is a good thing. I don't have near as much space between 3 and 12 as I had between 1 and 36. What would be next? 4 and 9. Narrowing the gap a bit more. And? Yeah, and 6 and 6 actually very nicely ends with us because they're exactly the same, so there's no space in between. A lot of times we get to the end and there's still space. It's just that what's in that space doesn't actually divide something. This one does. So our answer of the possible numbers of rows is all this list. So we could have 1, 2, 3, 4, 6, all listed just once, 9, 12, 18, or 36 rows. And it isn't so much that you have to do it in order, like these pairings like we did, but I really think that it just makes sure that you don't miss any, and it tells you when you're done. So it's a really nice organization strategy for doing these. And it fits right in with that theorem 414 about how they come in pairs, obviously, too. Okay, last one for today. Bob says that to check whether a number is prime, he just uses the divisibility rules he knows for 2, 3, 4, 5, 6, 8, and 10. He says if a number is not divisible by these numbers, then it's prime. How do you respond? Is his method going to work? That's really what you need to decide. Okay. Do you have an example, or can you think of an example in a way it fails, Kaylee?
Well, because it can be divisible, but it can still be like divisible by multiple numbers.
Okay, do you have an example, or can somebody help her with an example?
Like 12. Like say you tested it for 2 and it worked, but it also works for like 4.
Okay, So let's use 12 as our example. I don't think 12 is going to work with what you want, but let's help to figure out what it is we're missing. So if we had the number 12 and we used his process and we tested it and we said 12 divided by 2 and it divides, right? 12 divided by 2 is 6. Then his method would say, therefore, it's not prime because it divided by 2. That's what his method is. His method says, I'm going to take the number you give me and I'm only going to try it against these numbers. And if it doesn't divide by any of these numbers, then it's a prime number. What'd you say?
Well, I said yes. That doesn't work.
Does it?
Does it have to be divisible by all of them or just one
Nope.
of them?
If it's at least divisible by one of them, then it's not prime. Okay, so that statement's a true statement. If something divides by these numbers, it's not prime.
Yes. So,
But is this list of numbers enough?
um,
That's the question.
I
So,
don't know,
yes, because every number after that isn't just combinations of those numbers.
is
I
it?
can't remember the terminology.
Okay, I'm going to give you an example of a number
Okay. I thought the problem
that
was-
won't work with this list of numbers. Okay?
Okay.
But it's something you'll know what you need to do with it, I think. Okay, it divides by 11, right? And 7. But 11 and 7 are not on this list. So if he was given the number 77 and he tried his list of numbers here, it wouldn't divide by any of them. He would declare that this number is prime. Is it? No. 11 times 7 would actually be something that would not fit in with his category of numbers. So the idea of choosing a list of numbers is not a bad list, not a bad method, but his numbers that he chose are not sufficient. Not only that, but they're actually overkill in some ways in addition, they're overkill. Do you really need to check 8? No. If you already checked 2, you don't need to check 8. Do you need to check 10? No. Why would you not need to check 8 and 10 and 6 for that matter? They're already all divisible by 2. So in some ways, he's made things harder than he needs to because he's testing things that don't give him any new information. 8, 6, and 10 will not give him any new information. But he's also not testing all the things he needs to be testing. Right? So any number divisible by primes or a prime, and it's really 7 or bigger, say 7 or more, would be composite. But if they don't divide by the ones in this list, so by those in his list, he would incorrectly say it was prime. And then we're going to write that example down. Example, 77 won't divide by these numbers. But 77 is 7 times 11, thus composite. And I might also even put in a note, 6, 8, and 10 are, you can say irrelevant, they're overkill, they're unnecessary. I'm going to say not needed. in this list. And the real reason is because they're not prime. So that's not like the bigger issue. It definitely made something that you would have to test that was unnecessary. The bigger issue is simply that there's more prime numbers than the ones he wrote down. And the ones he wrote down, of course, are not already prime, but there's more than he wrote down.